This is Dr. Mohan Lakshmi, Professor and Head Department of ECE from Rohini College of Engineering and Technology, Kanyakumari District. So, in this video lecture, we'll see about the power MOSFET. So, power MOSFET are well known for superior switching speed and they require very little gate drive power because of the insulated gate. So, in this respect, power MOSFETs approach the characteristics of an ideal switch. So, the main drawback is on resistance and its strong positive temperature coefficient. A power MOSFET is a specific type of metal oxide semiconductor field effect transistor, which is MOSFET, designed to handle significant power levels. So compared to other semiconductor device such as an insulated gate bipolar transistor, which is shortly an IGBT or a thyristor, its main advantages are high switching speed and good efficiency at low voltages. The power MOSFET is the most common power semiconductor device in the world due to its low gate drive power, fast switching speed, easy advanced paralleling applied to the gate with respect to the source, that is VGS, gate to source voltage, with substrate and source grounded. Then negative charges are induced in the channel like a capacitor, and which will provide a current flow in the channel. So this shows you the structure which is shortly called as VDMOS, which is a virtual diffused power MOSFET. So you can see here there will be a gate width is represented, gate oxide is represented, then there will be the source. So this is the structure. So you can see here both here NPN structure, N plus and P N plus. So similarly there will be two layers, which is N minus and N plus. So here this is these points to be considered or and in the construction aspect. So parasitic NPN BJT. So it is held in cutoff by body source short, integral anti-parallel PN diode, extension of gate metallization over drain drift region. So the field plate and accumulation layer functions. So the division of the source into many small areas connected electrically in parallel. It maximizes gate width to channel length ratio in order to increase gain. So lightly dropped drain drift region, which determines the blocking voltage rating. So here you can see all the source gate conductor here. Still you can see all the charges mentioned over here as a layer. Okay, so here we have VGG 1 which is less than VGG 2 which is less than VGG 3. So here this is the diagram and this or the explanation. So when a small positive gate source voltage is applied to the capacitor structure, the positive charge and equal negative charge are on the both side of the gate oxide. So it will repel the majority charge carrier holes, thus exposes the negatively charged acceptor, which will create a depletion region. So further increase in VGS, so the depletion layer will grow in thickness and additional negative charge. So this begins to attract free electrons as well as repelling the free holes. So this will lead to an electron hole generation. So the layer of free electrons at the interface will be highly conducting and will have all the properties of an N-type semiconductor. Inversion layer, which is a conductive path and channel between N plus drain and the source. So here the threshold voltage is inversely proportional to the oxide capacitance per unit area. So which is Tox, it is represented as Tox, which is oxide thickness. So we are bothered about the on-state resistance. When the power MOSFET is in the on-state, it exhibits a resistive behavior between the drain and source terminals. So which is indicated as an RDS, that is drain to source resistance in on-state. It is the sum of many elementary contributions. So like RS, RCH, RA. RS is the source resistance. It represents all resistance between the source terminal of the package to the channel of the MOSFET. resistance of the wire bonds, of the source metallization, and of the N plus wells. RCH is the channel resistance, which is inversely proportional to the channel width. And for say given die size, to the channel density. The channel resistance is one of the main contributors to the RDS on of low voltage MOSFET, and it has been carried out to reduce their cell size in order to increase the channel density. RA is the axis resistance. It represents the resistance of the epitaxial zone directly under the gate electrode, where the direction of the current changes from horizontal, that is in the channel, to vertical, to the drain contact. Similarly, we have RFET or JFET. It is a determinal effect of the cell size reduction. The P implantations form the gates of a parasitic JFET transistor that tend to reduce the width of the current flow. And again we have Rn, which is the resistance of the epitaxial layer. So the role of this layer is to sustain the blocking voltage. Rn is directly related to the voltage rating of the device. A high voltage MOSFET requires a thick low doped layer. Okay, so Rn is the main factor responsible for the resistance of the high voltage MOSFETs. Rd is equivalent of Rs for the drain. So it represents the resistance of the transistor substrate and of the package connections. So switching operation. So because of their unipolar nature, the power MOSFET can switch at very high speed. So indeed there is no need to remove minority carriers as with bipolar devices. The only intrinsic limitation in commutation speed is due to internal capacitances of the MOSFET. So these capacitance may be charged or discharged when the transistor switches. This can be a relatively slow process because the current that flows through the gate capacitances is limited by the external driver circuit. So this circuit will actually dictate the commutation speed of the transistor. So assuming that it has sufficiently low inductance. Thank you.